Yeah, so I work in the IP Solutions division in Xilinx, and I'm working on an FPGA acceleration platform, a high bandwidth platform. So I'm just gonna give an overview of the platform, talk a little bit about the FPGA at the heart of the platform, some detail on that, talk about the build process and the user interface, some quality of results, and look at memory access performance. I suppose that's a key metric for this platform, and give a summary and talk about strategies to get the best performance from the platform. So yesterday there was a family of accelerators announced, the Alveo accelerators by Xilinx. They're based on the Vertex UltraScale Plus device. So this platform, the Alveo U280, is a kind of a sister card to those accelerators. It's based on an extended member of that family, the UltraScale Plus HBM family. So it's a VU37P is the device that's on the card. So that's a VU9P equivalent for anyone familiar with UltraScale Plus. So it has a huge amount of processing. So 1.3 megalots, 9K DSPs, large amount of embedded SRAMs, with the addition of 8 gig of high bandwidth memory. So as well as that, it has DRAM on board if you need depth. So there's 32 gigs, 2 channels. Host interface, Gen 3 by 16 lane, Gen 4 by 2. It's kind of a standard form factor for these cards. It's available in Vivado SDX in 2018.3. Boards aren't available for general use at that time, so their production release will most likely be 2019.1 timeframe. So in terms of what's in the FPGA, what's the FPGA floor plan? So the shell is what we term internally a tall and skinny shell. So it's a narrow strip down the side of the 3 SLRs of the device. The advantage in doing that is that you're leaving a large amount of resources free in each SLR. You're getting the best use of the device, and also you're not blocking use of DSPs and block RAM. So by doing this, you're actually only using LUTs and smaller amounts of block RAM. So the HBM, so it takes about 12.5% of the device area. So the HBM are at the bottom of SLR 0, and the access points to HBM. On the SLR boundaries, so it's important, we want to be able to talk to HBM from every part of the device. So you need a large amount of routing to do that. So at the boundaries, it's important that you have that. So there are 20K signals, 20K nets available between each SLR to route from a kernel, let's say in the top SLR, down to HBM. And there are DDR memory controllers. If necessary, these will be optimized out if you don't use them, and host accessible SRAM. So a little bit of detail about the device. So this is a kind of a marketing slide, but the main thing to take from this is that the DRAM stacks are integrated using chip on wafer on substrate, and there's a dedicated hardened interface to the HBM to maximize bandwidth and flexibility. So if we just talk about that hardened interface, so the key thing is that this isn't just memory. So there's a hardened PHY to talk to the HBM stacks. There are hardened memory controllers and the hardened switch network. So the interface in the fabric are 32 AXI masters connecting to the switch network. So basically the subsystem comes up by itself, it's self-initializing, so a user just needs to connect to those AXI masters. So the bandwidth on each of those masters is 14.4 gigabytes per second. There are 64 outstanding transactions on each master. That's important because more outstanding transactions, you get better performance. If there's latency in the switch, memory controllers need more outstanding transactions to reorder for random access. So the more outstanding transactions, the better. And there's a unified memory map. So each master has access to every memory in the stack. So physically, there are 2 HBM stacks. They're 4 gigs each with 230 gigabytes per second of raw bandwidth. There are 8 hardened memory controllers per stack, each with 64 deep reordering queues, and that matches with the outstanding transactions. Each HBM stack has 16 parallel pseudo channels. So a pseudo channel is 256 megabytes. There's 2 per memory controller, and each pseudo channel has a bandwidth of 14.4 gigabytes per second. So that's the theoretical bandwidth. And just a note on transactions, so 32 bytes is the smallest transaction size possible on a HBM PC. That's the JEDEC standard. So some notes on the switch. So the first note is a common technique used in switch design is SSID blocking. So this is a single slave per ID. So what this means is that a master using a single ID can only have outstanding transactions at a single slave. Okay, so for random access cases, that gives very negative performance. So if you're switching between multiple pseudo channels and you're accessing multiple pseudo channels from a master, that would give very poor performance. So that is the way the hardened switch is designed, and in fact the way most AXI switches are designed. So the solution to that is to include a soft IP. So there's a small soft IP, a random access master attachment. And this IP basically creates a multi-threaded stream from a single-threaded master. So it breaks AXI ordering rules, and then reorders in order to get the best performance. So this is a standalone IP. It's available for standalone use with this platform or with this device. But it's in acceleration platforms, the compiler, XOCC or SDX needs to be directed to include RAMA. So a second note on the switch. So the switch isn't a full 32-way crosspoint switch. It's actually composed of 8 4-way crosspoint switches. And between those, there are lateral links. So the lateral links don't have as much bandwidth as the internal 4-way crosspoint switches. So there are some lateral bandwidth limitations. So if I take masters 4 to 7 on the switch, if they're talking to pseudo channels 4 to 7, you get perfect switching. If I take masters 0 to 3 and they're talking to pseudo channels 0 to 3, you get perfect switching. If those 8 masters are talking to pseudo channel 21 to 23, you won't get the same performance as you would locally. Okay. So the solution to that is that the platform user provides, as part of the build process, the platform user provides the memories that it requires or the subset of PCs that it needs to access. So the platform can then choose the switch port to minimize the use of these lateral links, and as a result, it minimizes the congestion in the switch. So a final note on the switch. So there are 2 HBM stacks, and we've talked about I talked about switch as one large switch, but it's actually 2 switch components, and there's a limited write transaction rate through the crossing between the 2 switch components. So this is only for write transactions for 32-byte and 64-byte transaction sizes. So it's just there's no solution to this. So when coming up with a memory topology, if you're using smaller transactions, this needs to be handled in a user application. So in terms of the build process, so just looking at what happens under the hood when you're connecting a kernel master. So each master requires AXI width and clock conversion, a RAM IP for random access to improve random access performance if the master is random access. AXI bus pipelining, so you want to be able to connect a kernel from anywhere in the device to HBM, so there needs to be some kind of automated pipelining, and an optimal switch port connection to minimize congestion. So the acceleration tool SDX actually runs over Vivado, and this Vivado uses this HBM memory subsystem IP. So it's a soft IP that performs all of these functions. So it wraps the necessary soft IP. It exposes an API for the SDX compiler and linker. So the compiler and linker requests memory resources. The soft IP then chooses the optimal port connection, disables any unused HBM memories and ports to save power. And above that, XOCC accepts the user input, so it accepts the memory resources required by each master. It stitches the kernels into the dynamic region and attaches the memory resources by this Tickle API. So just to give a quick example, if we take a kernel in SLR, we want a kernel in SLR0, we want 16 AXI connections to HBM. All of the kernel ports need full access to the 32 gigabyte or 8 gigabytes of memory, and all kernel masters have a random access traffic profile. Yeah.
So I see that the masters are physically have different distances to the HBM memory. Does that influence the latency?
It will influence latency, exactly. And that's one of the reasons why you need a large amount of outstanding transactions. Yeah, you will have transactions in flight, but I mean the AXI protocol is split, so you send transactions, you don't wait for a response. So latency is overcome by having a large number of outstanding transactions.
So and the amount of transactions, in-flight transactions is different for different.
It will be different for different SLRs, exactly. Yeah. It's not significantly different. It would be of the order of a couple of cycles, a couple of pipeline cycles of the HBM clock. So just to look at the XOCC syntax to execute the example I talked about. So we have 16 ports. Each of those ports has a kernel argument. So we need to associate that kernel argument with memory resources. So in this case, we want to talk to all 8 gigs on all memories, so we need to specify that. So HBM 0 to 31 are all the pseudo channels. We need to place the kernel in SLR0, so this option places the kernel in SLR0. For this case, we don't need to. This is the default placement anyway, but as the device fills up, floor planning will benefit the clock frequency and performance. And we need to specify a user tickle file. So what this user tickle file does is it allows you to include RAMA. So basically in this, it's a single line of tickle to identify the master ports that are random access or require random access. So by default, there is no RAMA. So you need to include it if your master is random access. So just a note on allocating device buffers. So if you want to maximize access to a buffer, you need to spread this buffer across multiple HBM pseudo channels. So the HBM pseudo channel theoretical bandwidth is 14.4 gigs. If you've multiple engines trying to access this, you'll need more bandwidth. So you want to split the data across multiple buffers. So that's a manual process. So you need to specify at build time the correct access on the XOCC command line, and also you'll need to split the buffer in your host code. So actually create individual smaller buffers and allocate them to the different HBM pseudo channels. And just one note on Xilinx runtime. So the buffer can only be created up to the size of the HBM pseudo channel. So that's the maximum buffer size. If you have larger buffer size, you will have to split anyway. So some notes and constraints then on the build process. So at the moment, everything is done via DMA. There's no streaming kernels in this platform or in any of the Xilinx acceleration platforms. Up to 32 kernel masters can access HBM. So we recommend using only 31, up to 31. The reason is that one of those kernel ports will share with DMA. So, you may not get the performance you want either on DMA or on that kernel port. But as long as you're aware of that fact, you can use 32. Any kernels requiring access to both HBM and DDR need separate masters. So it's not a combined memory subsystem. If you want to share access to both, you may need to do mem copies, etc. And a kernel master can only access contiguous subsets of the HBM pseudo channels. That's just to make the platform easier. And by default, all kernel masters will access one HBM PC. So if you don't specify any memory resources for a particular argument, the platform will assume that you only want to use one HBM PC. The reason for that is just to minimize power to force users to plan memory and also to minimize power. And by default, all kernels are placed in SLR 0. So just to talk about compile time. So looking at the trivial example we had earlier of one kernel with 16 masters. So it's a real example of a kernel using kind of the standard clock frequencies of the platform. So HBM running at 450 megahertz, the kernel running at 300. The compile time is 3 hours. For larger kernels, for a stress test, so this is a customer design, so 12 kernels, each with a single master. The kernels are equally spread across all SLRs. Again, default frequencies, and the device is heavily used, greater than 60% on lots, so the compile time is 9 hours. So you should expect your design to fall somewhere in there between 3 and 9 hours of compile time. Okay, so memory access performance. So the baseline for memory access is point-to-point, so from a kernel master to a HBM pseudo channel. And if we look at that for linear accesses, for any transaction size greater than 64 byte for read-only and write-only, we get a 91% efficiency. So the bandwidth of one PC is 13 gigabytes per second. And the total system bandwidth is 419 gigabytes per second. For 32 bytes, this drops, so we only get 30% efficiency for a total system bandwidth of 144 gigabytes. The reason for that is memory controller design and the HBM typical timing parameters. So it's difficult in HBM with typical timing parameters to get above. In fact, the theoretical maximum is 50%. So with refresh, that brings it down to 40, and the memory controller inefficiencies bring it down to around 30%. So looking at random access, which is obviously a more difficult case, again, this is point-to-point. So if we look at transaction sizes of 128 byte or greater, again, we're looking at write-only and read-only here. We're not looking at turnaround time for read-write. So we get an efficiency of 60% on both read-only and write-only. And the total bandwidth is 275 gigabytes per second. Going down to 32 bytes, we see our 30% performance level again. So a total bandwidth of 144 gigabytes per second. So, so we've looked at standalone performance or point-to-point performance. So really, we need to look at subsystem performance as well. So what we've created a kernel that can assess subsystem performance. So this kernel executes different access patterns on different numbers of masters, different transaction types, so read and write, different AXI transaction types, different transaction sizes, and different addressing patterns, and using different memory resources as well. So for these experiments, RAMA was used in every master connection. So the random access IP is used in every master connection. So there's no SSID blocking. It's efficient for random access, and RAM has no impact on linear performance. So this may come as a tool eventually in SDX or Vivado to assess HBM performance. So I've taken one case. So this is actually a kind of a worst case, but I think it's interesting to look at and brings up a few interesting points. So this is a 32-byte random access case. And what we're doing is we're increasing the number of pseudo channels used and increasing the number of masters and looking at system bandwidth. Okay. So the important point is that every master has access to every pseudo channel. So on the switch, every node is being used constantly, so it's the worst case for the switch. Okay, so we have random reads on the left and random writes on the right. So we're plotting bandwidth versus the pseudo-channel count. So the first point to note is that performance scales linearly with a smaller number of PCs. So if you use up to 8 pseudo-channels and you're doing random access from 4 to 8 masters, you get 7 to 8 times better performance than one pseudo-channel. For write performance, it actually scales well up to 16 pseudo-channels. But once the number of pseudo-channels is greater than 16, the performance is bottlenecked by the crossing between stacks. So this is specific to 32-byte and 64-byte. For read performance, it also scales imperfectly. So for 16 pseudo-channels, we only see 11 times better performance than one. For 32 pseudo-channels, we only see 13 times better performance than one. Okay, so this is because of congestion and lateral links. Each switch port also has limited outstanding transactions. So if you have large latency, there is a blocking effect. If you have large latency due to congestion in the switch. Okay. So just to summarize, okay. So I focused on some of the negatives. All right, just to show that the memory system is complex and needs to be experimented with to get the best performance. But in general, there's a huge amount of bandwidth for very little effort and very little impact on the free platform resources. So everything's hardened, so you get this essentially for free. There's a huge amount of flexibility in the access patterns, but because of that flexibility, there is maybe some work to be done depending on your memory access topology. So you may need to spend some time optimizing to get the best performance. A basic, the most obvious thing is to use as many HBM pseudo-channels as necessary in parallel. That may need some experimentation to figure out. Any kernel master should have a large number of outstanding transactions. So at least 64 outstanding read and 32 outstanding write. More than this for random access. So if you're using the RAM IP with reordering, you may need more. We used 128 in our test cases. And be aware of the unexpected behavior. So 32-byte transactions have poor efficiency. That's the nature of DRAM, smaller transactions. So if possible in your application, use larger. And avoid routing small write transactions across the boundary. That's a Xilinx specific thing. So that was all I had.